Hello and welcome to another in a series of videos in which I'm building experiments from this book, Make Electronics by Charles Platt, the third edition. Now just to reiterate, these videos are not sponsored or supported or endorsed in any way by the publisher or the author. They're just me as a hobbyist expressing my enthusiasm for the book and showing the results of my builds. So I do encourage you to buy your own copy if the experiments look like the sort of things you'd like to build. Now in the previous episode we were introduced to the first integrated circuit in the book, which is the famous 555 timer chip, and I made a couple of the circuits in the book and demonstrated a couple of the modes of that chip. Well, there are still more modes to explore and we will be doing that in the experiment today.
Okay, so once again we have a new circuit with our 555 timer chip at the center. And the first thing I'd like to point out is that whereas before our output pin, which you'll recall is pin 3, was used to light an LED, in this case we have it connected to a speaker. So what else has changed on this circuit? Well, let's look at the things that are the same first. So obviously pin 1, which is our ground, is connected to ground. Pin 8, which is our VCC pin, is connected to our positive supply rail. We do still have our resistor capacitor network connected to pins 6 and 7, which you'll recall are the threshold and discharge pins. One thing you will note is that the values are different. Before we had an electrolytic capacitor here, now we've got a much lower value ceramic capacitor. And that's because, of course, before we wanted the LED to come on for a matter of several seconds, so we needed a long delay. In this case, because we're trying to drive a speaker, we want a much higher frequency. And hence the change in those components so that we achieve that higher frequency, because of course we want it to be somewhere in the audio frequency range in order to drive the speaker and for us to be able to hear the result. So what's changed here? The first thing is that we've got no momentary switches as we had before. So rather than a momentary switch that was used to ground the reset pin, we now have the reset pin connected directly to the positive supply rail, which of course means that it will never be activated. We're just holding that pin high. The other thing you'll note is that before, where we had another momentary tactile switch which was connected to pin 2, which is the trigger, we now have pin 2 connected directly to the threshold. And that's because this form of wiring up the 555 is yet another mode, which is called the astable mode. Now you'll recall that in the previous circuit, pin 2 was connected to the positive supply rail via a pull-up resistor, which kept it in a high state until we pressed the momentary tactile switch to ground it, which triggered the circuit. Now in this case, because we have that direct connection between the threshold pin and the trigger pin, you'll recall that what happens at the threshold pin is that we're monitoring for the voltage to reach 2/3 of the supply voltage. And at that point, the discharge pin, pin 7, is reconnected to ground and the output pin is sent low. Of course, when that happens, the capacitor will discharge, which means the voltage present at pin 6 will drop. And because we have that direct connection with pin 2, that will also be the case at pin 2. And when that voltage drops, that will in fact trigger the circuit. So what will happen is we'll start again. The output pin will be sent high. The discharge pin will be disconnected from ground, so the capacitor will begin to charge. That starts this endless cycle where the output pin goes high, the capacitor charges up, gets to 2/3 of the supply voltage, the output pin gets low, the capacitor begins to discharge, and when it gets to a low enough voltage, it re-triggers the circuit. So the other difference is you'll notice there is now an additional resistor between the discharge pin and ground. And the reason for that is because we don't want the capacitor to discharge immediately. We want to slow down the rate of discharge so that we get a gap before we get the next cycle where the output pin is high. So this way we'll get a nice even waveform where the output pin is driven high for a short period, goes low for a short period, and then is driven high for a short period. And you might recognize that what that will do is generate a nice square wave across the speaker and give us a tone. So that's enough theory. Let's plug the circuit in and see what we get. So there we go. There's our tone. Nice square wave. And as before, we have a little trim pot here in the RC network. So we can use this to get a lower tone if we increase the resistance. Or we can go back the other way. To get something quite high frequency and very unpleasant. Oops. Yes, you'll notice there that the one thing I find with these trim pots, let me just unplug this so you can hear me. One thing I have found with the trim pots is that they don't, at least mine, don't want to stay in the breadboard particularly well. So if you build this and you find that you're not getting any sound at all, the first thing I would look at is whether the trim pot has come loose. And what I found is just pressing that down to make sure there was a solid connection there did the trick. But you would have noticed there as I was actually adjusting it, I was starting to lose the connection a little bit. So you do have to take a little bit of care with it. Okay, as before, let's take a look at what's going on with the oscilloscope so we can get a bit more intuition about what's happening in the circuit. So I've got the oscilloscope probes connected exactly as I had them for the circuit in the previous episode. So I've got one probe connected to the output pin, pin 3, and another probe connected to the positive side of the capacitor in the RC network. So let me just plug the battery back in and let's see what that looks like. So what you can see here, let me turn this off. What you can see here is that here's our output pin, and you can see we're getting a square wave there, and you can see how that is corresponding with the charging and discharging at a fairly regular rate of the capacitor. Now earlier I said that we were generating a square wave which looks like this. And that's not strictly true. What we're actually generating is a pulse wave, because a square wave is a very particular form of pulse wave where the amount of time that the wave is in the high state compared to the amount of time that it's in a low state within a single cycle is equal. And that's referred to its duty cycle. And to qualify as a square wave, it has to have a duty cycle of 50%. And as I said, what we're actually generating is a pulse wave. And the reason it's a pulse wave rather than a square wave is because the amount of time that the wave spends in the high state compared to the low state within a single cycle is greater than 50%. Now, of course, with a pulse wave, it could be the other way around. It could be that the amount of time it's in the high state is less than 50% compared to the amount of time that it's in the low state. But in our case, it's this way round. We're keeping the wave in a higher state for longer than we are in a lower state within a single cycle. So assuming that what we wanted to do was to generate a square wave rather than any other kind of pulse wave, what can we do? Well, the book does have a solution for this.
So what we're looking at here is our current circuit, or at least we're looking at the RC network portion of the circuit. And as you can see here, what we have is a fixed value resistor that sits between the positive supply rail and the discharge pin. Then between the discharge pin and the threshold pin, we have another fixed value resistor. It's the same value as R1. And we have a variable resistor so that we can change the frequency. And then of course below the threshold pin we have our capacitor, and the other side of that is connected to the ground rail. So what is the issue with this configuration of the circuit? Well, if we look at the charge path, you can see that it passes through both R1 and R2 and the variable resistor before it reaches the capacitor. So all three of those resistances are going to be adding up to set the charge rate. Compare that to the discharge path, and that only passes through the variable resistor and R2 before it goes to the discharge pin, which at this point of course is connected to ground. And so you can see, I hope, that because the resistance is larger, it's always going to be larger no matter what the variable resistor is set to. Because the resistance is larger for the charge path, the charging rate is going to be slower than the discharge rate. So what can we do about that? Well, one thing you might think is, okay, well, let's take the variable resistor out of the equation, and then we've got two equally matched resistors either side of the discharge pin. Well, that is true, but it still leaves us with an issue. It doesn't completely solve things because of course our charge path still goes through both resistors, whereas our discharge path just goes through R2. So we're still going to have a longer charge rate than a discharge rate. So it hasn't entirely solved our problem. So the solution presented by the book is to add in what's known as a diode, and a diode is a semiconductor, and we've already seen one form of diode in the form of the light emitting diode, of course. But in this case, our diode has one job, which is to allow current to only pass in one direction, which is indicated by the arrowhead. And remember here that we're talking about conventional current. So what will happen now is that during the charging of the capacitor, that the current will flow through R1, through the diode, because of course it allows current to pass in that direction, and then to the capacitor. When we come to the discharge part of the cycle, the current will flow through R2 only to the discharge pin. It won't be allowed to travel back through the diode because of course the diode blocks current flow in that direction. So the only path it can take is through R2 to the discharge pin, and then of course to ground. So in theory, this gives us our square wave. And I say in theory because of course while nominally R1 and R2 do have the same value, practically speaking they won't of course be exactly the same. There will be some difference between them. So we won't get a perfect square wave. It's very difficult to achieve a perfect square wave, but we will get something much closer to an ideal square wave than we had with the previous circuit. Okay, so let's build it.
Okay, so here's our revised circuit, and what you'll be able to see is the variable resistor. We'll be using a trim pot for that. That's gone, and instead we've got this diode. Now, all diodes fundamentally do the same thing, which is to prevent the flow of current in one direction. There is a special type of diode, as in a diode, which is a little bit more exotic, but we won't go into those. But generally speaking, they all do the same thing. And The difference between them is just that they have different characteristics based on their application. Now, this particular diode that we're using is a signal diode, and what that means is that it's designed to work with fairly low currents, but it can cope with high frequency switching, which of course is ideal because that's what we're doing in this circuit. We are switching states at fairly high frequency, well, high enough anyway to drive a speaker. So a signal diode is ideal. There are other types of diodes like rectifier diodes, which no doubt we will come onto at some point. But for now, this one is ideal for our purposes. And as I explained in the circuit diagram, it is just bypassing this resistor when we're charging up. So when we're charging up, the path will be through the first resistor here, then through the diode, and then to the capacitor. Okay, so let's plug it in and see if we get our square wave. And nothing. So have I made a wiring mistake somewhere? I'm pretty sure that I haven't. It all looks good to me. It might be a loose connection, but you know what I suspect? I have my suspicions. Do you remember, if you saw the previous video, you might recall that when we had the trim pot turned right down to the minimum setting, that we were getting an extremely high frequency. It was very, very shrill. And my suspicion is that because we're now, we're basically just using the base resistors, and this is just a 10K resistor here on either side, my suspicion is that the frequency is actually just too high to hear. So right now, I'm probably driving every dog in the neighbourhood crazy because they might be able to hear it, and maybe a few young children as well because their hearing isn't shot like ours. But it's certainly too high frequency for me. So if my suspicion is correct, what I should be able to do is substitute those two resistors for a higher value, which will lower the frequency to something that we can hear. So let me try that now. Okay, so this is exactly the same circuit, except for I've substituted the 10K resistors we had there previously for a couple of 100K resistors. So let's see if that makes any difference when I apply power. Yes, there we go. So my suspicions were correct. So that is a square wave. Not sure that I could say that I could really tell any difference between that and the pulse wave, but there you go. Let me unplug this because it will annoy everybody. It's certainly annoying me already. But that was the issue. So if you're building the circuit from the book yourself, you might well, depending on how good your hearing is and what speaker you're using, you might well have the same issue. So if you do, where you build the circuit and you're not apparently getting any output, my suggestion would be try a higher value of resistor to give you a lower frequency. That was 100K, but probably the trim pot that we had in there previously was 500K, so you could go up as high as 500K, and you should be able to get an audible result. But let me know in the comments how you get on. I'll be interested. Okay, yet another new circuit. Well, not completely new, but a modified circuit. So you may recall, if you watched the previous video, that there was one pin which we weren't really using. We just had it connected to a coupling capacitor, and that was pin 5, which is the control pin. So it's about time that we gave it something to do. And so the book introduces us to another modification of the circuit, So what pin 5 will do is allow us to fine-tune the frequency when the 555 is in a stable mode. And what you can see here is that we've actually got that pin now connected to the wiper pin of a trim pot. Now, the thing to note here is that here we are actually using it as a potentiometer and not as a variable resistor as we were doing with the one over here. Here we just connected 2 pins. We connected the supply to the outer pin, and then we're taking the signal from the wiper out. So it's just acting as a variable resistor. Here we've connected both of the outer pins. And there's a very good reason for that, which is that the control voltage has to be within a certain range of the supply voltage for pin 5 to work properly. And so here we've got things set up as a voltage divider. So when you have resistances, fixed resistances in series, the voltages that you measure across them will be proportional to their resistances. So here we've got a 1K resistor from the positive supply rail, a 1K resistor from the negative supply rail connected to either ends of the track on the trim pot. And then the wiper is being fed into the control pin. So what this means is that effectively those 2 resistors are setting the lower and the upper voltage that we will get across the trim pot. And then the exact voltage we get between those limits will depend on the position of the wiper. So how does this help us? Well, as I said, it allows us to tune the frequency, of the 555 in a stable mode. And you may well ask, well, hang on a second, isn't that what this variable resistor is already doing? Well, yes, it is, except that this variable resistor is effectively adjusting the charge rate of the capacitor. And so it's affecting the frequency that way, whereas this is affecting the voltage going into the control pin. So what it will effectively give us is a fine-tune control. So let me put some power in and let's actually hear it in action. So just to reassure you that things are still fundamentally working as they were, I can adjust this variable resistor here, to adjust the base frequency. Let me put it back in the middle somewhere. But here, by changing the voltage going into the control pin, we can fine-tune it. Sorry, that slight warbling there was because I was breaking the connection. So if I move this up to a higher base range, hear the effect that's having? That effectively this is setting the base frequency and then we're fine-tuning it with this. We're getting slightly variable results here because obviously I've got a bit of a loose connection. But hopefully you can hear fundamentally how that is working. Okay, final circuit for this experiment, I promise. So what have we got going on here? A second 555 chip. And the way that this is connected up is that this 555 has got a very similar circuit to the other one, albeit with different value components. But its output is actually what is being fed into the control pin of our first 555. So effectively, we've got an oscillator controlling an oscillator. And once again here, we've also got a way to control the frequency of this oscillator using a potentiometer feeding into the control pin on this 555. So what we're going to end up with here is that we'll have one frequency modulating another. And if you are an analog synthesis fan, and I'm sure at least some of you are, you might recognize this setup. And very often you'll get a setup where you have one oscillator modulating another. Sometimes it will be a low frequency oscillator. Other times it will be, two oscillators with the same frequency range but still modulating each other. So that is effectively the setup we've got here. So let me plug it in and let's see how it works. And I hope I get some sound this time. Oh, that doesn't sound hopeful. That doesn't sound hopeful. It'll be one of these trim pots, I tell you. They're a pain. One of them will be causing the problem. Oh, look, there you go. That's how easy they come out. Let me just see what is... Yeah, there you go. I knew it would be. Honestly, they are a pain. So what you can hear is that we've now got that rising and falling frequency, and that's because this 555 is modulating the frequency of this one via the control pin. So once again, I can adjust the base frequency. And you'll see that we've got two trim pots going on here. So this one is controlling the frequency of the second 555. So you can hear as I turn that up, how the rate of that warbling changes. And this one is controlling the amount of modulation that we're getting. So if I turn this down, can you hear that the amount of modulation is decreasing? That's interesting. And then we can ramp it up. And once again, we can adjust the frequency of the modulation. Almost to the point where we're getting a continuous tone again. So there you go. Throw away your Moog. You've built your own. No, seriously, don't throw away your Moog, whatever you do. Yeah, there we start to see how versatile the 555 is, especially when you start using more than one of them.
I hope you enjoyed that. I certainly had fun with it. Please do join me for the next episode when we'll be continuing with the 555 timer, but introducing circuits with multiple 555 chips and also taking a project from the breadboarding stage through to a final build in a project box. See you then.